22. Okay. So, hello everyone. So, yesterday we had a lecture on science and technology. So, that was an introductory lecture. And in yesterday's lecture, we discussed about like various important things like how the universe was formed. We have gone through some religious views also, and we have also understood about the scientific view related to the how the origin of the universe happened. We understood about, let's say, a concept which is known as Big Bang theory, and after understanding the concept Big Bang theory, we have understood about related concepts. We have understood about, let's say, a law that was given by which scientist? No. Yes. Tell me. Hubble's law. We have understood about Hubble's law, right? And apart from this, we have understood various related phenomena, okay, related to how the universe was formed. We have understood about, let's say, Doppler's effect also, right? We have understood red shift and blue shift, right? We have understood about, let's say, singularity, the concept related to singularity, how the universe was formed, right? The black hole event. We have seen the time horizon of the universe. We have seen that the universe is still expanding, right? We have seen the universe is still expanding, and those galaxies that are far away from us, the galaxy which is very far away from us is moving at a faster rate away from us as compared to a galaxy which is nearer to us, right? So, this was talked by Hubble. Hubble has, let's say, mentioned this thing in his law. So, today what we are going to do is like we are going to further our understanding. We are going to understand little more related to how the universe was formed, and yesterday we started the discussion related to theories of relativity, right? So, we discussed about special theory of relativity, we discussed about general theory of relativity. However, let's say like yesterday we did not discuss in detail about general theory of relativity. Although special theory of relativity I have discussed, let's say, in the past also. However, today also I am going to touch upon it because the concepts are very deep. It requires deep understanding, deep knowledge, right? Earlier you have read it in the, let's say like we have discussed in the demo class also. But maybe, let's say like you may be needing one more, what we say, like, one more reiteration of the same thing. So, today, let's say our idea of covering the things is we are going to understand about special theory of relativity, we will learn about general theory of relativity, then we will learn about black holes, how the black holes are formed. We will understand, let's say, some counterintuitive effects related to theories of relativity. We will understand gravitational time dilation, gravitational length contraction, mass energy equivalence. We will understand similar phenomena associated with this. Then we are going to understand about the composition of the universe. I mean, like what proportion of the universe is constituted by normal matter, right, as we know today, as we can see, and what proportion of the universe is composed of dark matter and dark energy. That's also we are going to understand. Then we are going to understand about a concept which is known as scientific social responsibility, right. So, we will understand what is the importance of that concept. So, let us start the discussion with the first topic, right. So, name of the topic will be topic number 1. It is spatial theory of relativity. Quickly write down spatial theory of relativity. There are some important things related to this. Number 1, who has given the spatial theory of relativity? It was given by Albert Einstein. Okay, so spatial theory of relativity was given by, let's say, it was postulated by Albert Einstein, right? Albert Einstein. So when he postulated this thing, he postulated this in 1905, and that time he has come up with a research paper. It is also important for you to know the name of the research paper, right? It is also important for you to know the name of the research paper. What is the name of the research paper? So he has published a research paper, right, back in 1905, and name of this research paper is very important, right? So it is known as the electrodynamics of moving bodies. Name of the research paper is the electrodynamics of moving body. This was the research paper that Albert Einstein has published in 1905, where he has talked about a spatial theory of relativity, right? So today we are going to understand, let's say there are two postulates based on which, let's say, spatial theory of relativity is based, and we are going to understand what are its impact, what are its effect. And based on its impact, based on its effect, UPSC has asked question in the past, and UPSC is likely to ask question in the, let's say, future also, right? And so far, after Albert Einstein has given this theory in 1905, it's been more than 100 years, right? Still, let's say, no further work has been done, in the sense that, he was very futuristic, right? Way back at that point of time, he talked about a spatial theory of relativity, he talked about general theory of relativity. That has actually challenged the scientists across the world, that has challenged the scientific understanding related to how the universe works, right? What are the forces that are there on the universe? Before Albert Einstein has postulated this thing, Newton, Sir Isaac Newton has given the laws of gravity. We know the 3 laws of gravity as we discussed yesterday. So those laws of gravity were based on the idea that any body, any object, right, that has mass will have force of gravity. Means any object that has mass will attract every other object with some force, that is known as force of gravity, and I have talked about the formula also. But here, through the spatial theory of relativity, Albert Einstein has talked about that why the gravity, the concept of gravity is different from the idea that was postulated by Sir Isaac Newton. So today we are going to understand about the fabric of space-time. What? We are going to understand about the fabric of space-time. What do we mean by space-time fabric? And what role does it play, right, in, let's say, in gravity in the body. So that's important. So write down this, he has published a research paper named The Electrodynamics of Moving Body. Now, after this, write down few points related to the spatial theory of relativity. You have written all of it. Write down the spatial theory of relativity. The spatial theory of relativity is a scientific theory. Proposed by Albert Einstein. Good afternoon, everyone who have joined online. Ritu, Vidya. All right. So, the spatial theory of relativity is a scientific theory proposed by Albert Einstein in 1905. Full stop. It is based on 2 postulates. What? This spatial theory of relativity is based on 2 postulates. What are those 2 postulates? Number 1. Write down. The laws of physics are same. The laws of physics are same for all inertial reference frames. The laws of physics are same for all inertial frames of reference or inertial reference frames. For all inertial frames of reference. Number 2. So before we go ahead to understand this, you need to understand that what laws of physics are we talking about. So we know physics is a branch of science that deals with how objects work, right, naturally, right, in the universe. Means if we talk about gravity, if we talk about acceleration, if we talk about force, if we talk about momentum, so some laws of physics are applicable over there. So here Albert Einstein says that the laws of physics are same for all, let's say, all inertial frames of reference. What do we mean by inertial frames of reference? That's also an important point of discussion. Inertial frames of reference means, let's consider if we are observing anything for example, let's say like, we conduct race, F1 formula race. So there, like, we see how the, let's say, how the cars are moving, right? So the cars are being seen with respect to one another, and we see the goal post where the car will go. So that's the frame of reference, like, what we are seeing. So in that particular view, what we are including, that is important. So in the inertial frame of reference, we can have planets, we can have solar systems, we can have, let's say, bodies, like, bodies in the sense like human being can be there, car can be there, anything which is under observation, anything which is under observation. So that will be a frame of reference. But what do we mean by inertial frame of reference? Inertial frame of reference means that in this frame of reference, the bodies that are moving, right, these bodies will be will either be at rest or they will be moving relative to one another with uniform velocity or uniform speed. Means, let's say, here I am talking about that I have a car. Okay, this car is moving in this direction, let's say. Okay, and then there can be a person. This person may be, let's say, like, standing. So he is at rest, the car is moving. So the thing is, car is moving, car should be moving, let's say, with some uniform velocity, right? That's the thing. So this is known as inertial frame of reference. So here Albert Einstein says that, like, the special theory of relativity is based on two postulates. One of the postulate is the laws of physics as we know today. All the laws of physics are same for all inertial reference frames. Apart from this, the second thing is the second postulate. Write down the second postulate also. It says that the speed of light in vacuum, the speed of light in vacuum is constant. The speed of light in vacuum is constant. And what is the value of the speed of light in vacuum? I discussed yesterday, it is denoted by the letter C, which is almost equal to 3 into 10 raised to power 8 meter per second. This is the speed of light in vacuum. What do we mean by vacuum? In the outer space, in the space where there is no medium. So the speed of light in that medium will be this thing. This will be the value. Per second it's going to travel these many meters, 3 into 10 raised to power 8. 10 raised to power 8 means you are multiplying 10, right, 8 times. That will be 10 raised to power 8. So this is the thing. So after this, write down the speed of light in vacuum is constant and independent of the motion of the observer. And independent of the motion of the observer. And independent of the motion of the observer or the source of light. Or the source of light. Are you understanding? So speed of light in vacuum will be constant and it will be independent. For example, there are observer, right? So we discussed about what? Earlier we discussed about this. What effect? We discussed about Doppler effect. We discussed about perceived frequency, red shift, blue shift, etc. Right? So here what he is saying that the speed of light will be same, right? Irrespective of the, let's say, like, motion of the observer or the source of light. Observer means someone who is observing source of light from where light is being emitted. This is the thing. This is what he says. So these are the two things that he has said, and from these postulates, write down from these postulates, after this, write down. From these postulates, Einstein derived a number of surprising and counterintuitive effects. From these postulates, Einstein derived a number of surprising and counterintuitive. You can write down consequences or effects. Counterintuitive effects. What are these effects? Number one is, write down, time dilation. Number one, time dilation. Write down time dilation. What do we mean by time dilation? First of all, you need to understand, right? What do we mean by time dilation? To understand time dilation, I'll give you an example. This example is known as twin paradox. What? It is known as twin paradox. Like we discussed it earlier also, let us quickly understand. Let's consider there are two brothers. These two brothers are on the surface of the earth. They are on earth. Okay, they are twin brothers. So what is happening? One of the brother, let's say, goes on a spaceship. Okay, one of the brother goes on a spaceship. Right? And after couple of years, he comes back. So this brother who was on a spaceship, right, he traveled, right, he was at a speed, right, but this brother who was on the earth, he was on the earth. So after he comes back, the person who was on earth, this person seems to be more aged as compared to the person who has traveled. You are understanding? So let's say brother 1 who stayed back, brother 2 who went. Brother 2, when he came back, let's say, like, before they went, let's consider they each had age of 30 years. So he came back after 30 years. So the thing is, like, this brother now looks like, 74 or 75 years. And second brother looks like 60 years. This is the thing. So for him, the time was passing slowly as compared to the brother who stayed on the surface of the earth. This is known as time dilation. This is known as time dilation. So write down about it. So clocks moving related in front of time dilation. Write down. Clocks moving relative to an observer. Clocks moving relative to an observer appear to run slower. This means that a person traveling at high speed, this means that a person traveling at high speed will experience time slower, than a stationary observer, and full stop, write down. This has been experienced, or this has been observed in experiments. This has been observed in experiments with high speed particles. Okay. This has been observed. So now, what is the name of that experiment? So there are experiments that are going on across the world. What they do, they accelerate the particles to a very high speed. Why do they accelerate the particles? They accelerate the particles to, let's say, like, understand about behavior of some subatomic particle inside those particles, to, let's say, identify whether new particles are still there that we have not yet discovered. So one of the name of the particle accelerator is known as Large Hadron Collider. Okay, Large Hadron Collider. Name of the, let's say, like, particle accelerator is Large Hadron Collider. So where is this Large Hadron Collider located? This is located at CERN, C-E-R-N. Okay, so this is like European, some European Commission for, let's say, nuclear research. Okay, so they named, like in French, they have written it that way. Okay, CERN. So this Large Hadron Collider is found over there, and they accelerate the particles to very high speed, because at a very high speed what happens, the behavior of the particle changes. So they start understanding those particles, and this is the time dilation is, let's say, has been observed in experiments. Okay, so this is one of the effect. Did you understand what do we mean by time dilation? Time dilation means an observer, who, like a person who is moving at a high speed. For him, he will experience the time to be passing slower as compared to a stationary observer. Right? If a person is stationary, for him the time will pass faster as compared to a person who is moving. You are understanding? This was the first thing. Second thing, write down, second point is length contraction. What? Second is length contraction. Length contraction. So what is length contraction? Again, to understand about length contraction, we need to, let's say, have a kind of inertial frame of reference. In that inertial frame of reference, one will be observer, other will be moving. And the, let's say, like the object or the person who is moving, right? The moving object or person will appear to be smaller, will appear to be shorter as compared to an object which is at a stationary, which is at rest. Means like an object which is moving, which is coming towards us, right, in the direction of us, will appear to be smaller as compared to an object which is, let's say, like at rest. This is the thing. So this is, you have written length contraction. So length contraction, write down about it. Objects moving related to, objects moving relative to, objects moving relative to an observer appear to be shorter in the direction of motion. Appear to be shorter in the direction of motion. Let's consider this is the object which is moving. It is moving in this direction. So if there is an observer, so if this object is moving towards the observer, right, it will appear shorter than its actual size. It will appear, it will not become shorter. It will appear to be shorter. That is known as length contraction. Is it understood? It will appear to be shorter. That is known as length contraction. So write down after this, right? You have written a sentence. After this you write, this means that a fast moving object, this means that a fast moving object, this means that a fast moving object will appear shorter than the same object at rest. Will appear to be shorter than the same object at rest. This effect has also been observed in experiments. Write down third. Third is known as mass energy equivalence. Mass energy equivalence. Okay. Mass energy equivalence, there is an equation. This is known as E equals to mc square. M, what is C here? C is speed of light. What is M? M is mass of the object. What is E? Energy. E is energy. E equals to mc square. This equation is known as mass energy equivalence. However, write something about it. Okay, write. E equals to mc square, and after this write all of it. This equation shows that mass and energy are interchangeable. Mass and energy are interchangeable, and that a small amount of mass can be converted into a large amount of energy. Into a large amount of energy. Into a large amount of energy. Now, have you written this point? Now, focus on the board here. Let's consider there is an object. I'll make you understand what do we mean by mass. Okay. So, there are many students in the classroom. So, can anyone tell me what is your mass? Maybe this is person A. Just for let's say for our understanding. Yes. Anyone knows his or her mass? No. Okay. Tell me anyone who can volunteer. Yes. 50, 70, 62, 70. Okay, all right. So whatever you are saying, this is weight. Okay. So whatever you are saying, this is known as weight. But mass is a different quantity, right? Weight is equivalent to force, right? Force is equal to mass into acceleration. And here we are on the surface of the earth. So since we are on the surface of the earth, if we have a, let's say if we have a weighing machine, so we stand on the weighing machine, it says that you are 80 kg, you are 70 kg, you are 50 kg, like that, right? But the kg that it is saying, actually it is talking about the weight that we have. It also accounts this acceleration. Acceleration due to gravity is g equal to 9.8 meter per second square, right? And whatever weight you are saying, somebody has 80 kg. So 80 is equal to your mass into 9.8, right? So mass will be 80 upon 9.8. Like in place of 80, put your weight. That will be your mass, right? So mass is a different quantity. So mass is calculated in kg. Mass is calculated in kg. Weight is equivalent to Newton. Mass into acceleration, force, Newton, like that. Okay. So this is the, let's say this is the mass of a body. This is our mass. So here the equation that Albert Einstein has given, which is E equals to mc square. Here now you understand. Let's consider someone, let's say someone in our classroom has a weight of 98 kg. Let's consider me, like I will be needing a smaller kid also with me to weight 98 kg. So 98 kg is my weight. My mass will be 98 upon 9.8 will be equal to 10 kg. What? My mass will be 10 kg. So let's consider 10 kg into c square. That will be the amount of energy that I'll be drawing. What is c? C is equal to 3 into 10 raised to power 8, right? Meter per second. So if we make a square of it, this will be 9 into 10 raised to power, right? 8 into 2, 16, right? Meter per second square, like that, or meter per second. It is means like any quantity you are multiplying with square of speed of light. I mean like the energy that you are going to get will be very high. Are you understanding? Only 10 kg of mass can be converted into huge amount of energy. And this is what is used in nuclear reactors. In India, across the world, we have nuclear reactors. In nuclear reactor, why we are using nuclear reactors? We are using for generation of power. And nuclear energy is known as dual use technology. Using nuclear energy, you can create nuclear weapons that will be used for military purposes. Using nuclear energy, you can create, let's say electricity that will be used for civilian purposes. So that's why it is known as dual use technology. It does have military applications, it does have civilian applications. So in the power plants that we have, we generate electricity, and the kind of electricity that we generate, there we use nuclear fuel. For example, we use uranium-235, we use plutonium-238 and plutonium-239. So these are known as nuclear fuel. So these are big atoms. What happens in nuclear power plants, right? These big atoms, we bombard these atoms with neutrons. Neutrons are chargeless subatomic particles. They do not have charge. They do have mass. So when they strike over here, they break down the big atoms uranium or plutonium. After they break it, so it splits into two different atoms and it releases huge amount of energy. That huge amount of energy that it releases, that energy is used for, let's say, running the turbine and generating electricity. Are you understanding? So this is the thing. So because mass energy equivalence has been told, right, by Albert Einstein, that's why we see usage of nuclear powered plants in the world. That's why atom bomb has been created. And there is a very good story associated with Albert Einstein. What is that story all about? That story is long back, right, when World War II was going on. At that point of time, Albert Einstein was a very renowned scientist. Like, he was internationally acclaimed scientist, right? And so there was a person who approached Albert Einstein. Why did that person approach Albert Einstein? Because he was fearful that Germany was developing atom bomb. He was fearful that Germany was developing atom bomb. So he wanted to reach out to Albert Einstein to seek his help so that, like, United States of America can build atom bomb. Okay, so like, Albert Einstein used to live in Princeton, New Jersey, which is in United States of America. So name of that person is Leo Szilard. Okay, Leo Szilard. So Leo Szilard, what he did, he approached Albert Einstein. Albert Einstein has written a letter, right, to the President of the United States of America. His name was Franklin D. Roosevelt. Okay, like President Franklin D. Roosevelt. So after reading his letter, right, so Franklin D. Roosevelt later on has, let's say, approved the project which is known as Manhattan Project, as we discussed earlier. So Manhattan Project was a project under which they developed atom bomb. They have developed, let's say, little man and fat boy. They have named those atom bombs like this because one of the atom bomb worked on uranium, other worked on plutonium. Huh? They were working really on it. So Germany was really working, and Germany was one of the most powerful country at that point of time. It was powerful and it was fearless. In the sense, they had power and they were fearless also. They were attacking on different countries. Okay, so this is the thing. So United States of America wanted to, let's say, safeguard its, let's say, defense thing. So that's why they have developed it and they have launched it on Japan, right? So after then, so they have launched one of the bomb on 6th of August, other on 9th of August. In Hiroshima, 6th of August, Nagasaki, 9th of August. And after few days, Japan has unconditionally, let's say, unconditionally, they have said that, we don't want to fight any further. So they have accepted their defeat in the World War II. This is the thing. And long before that, Germany has also, let's say, surrendered. Japan has surrendered, Germany has surrendered, and that ended the World War II. Okay. So technology plays a very important role in people's lives, right? Technology can be used for good purposes, can be used for bad purposes. However, let's say, Albert Einstein had just written a letter. And Albert Einstein was a very good scientist, right? So because of his letter, it led to the, let's say, Manhattan Project, right? Later on, Albert Einstein has regretted that, why did I write that letter? Because of this, let's say, it led to the creation of atom bomb, and this is destructing the entire world. Okay. After World War II, he became a proponent of peace. He said, atom bomb should not be used. And even the person who was director of the Manhattan Project, Oppenheimer, he also, let's say, regretted after building it, right? So this is the thing. So that's how things happen. So here what we have understood, three counterintuitive effects. One is time dilation, other is length contraction, third is mass energy equivalent. Time dilation means an observer which is at motion will experience the time to pass slower as compared to an observer which is at rest. Are you understanding? If we have to apply it on satellites, let's consider we have satellites and these satellites are put, okay, let me talk about, let's say this is Earth and then we have satellites, and these satellites are, let's say, revolving around the earth. So a person who is on the earth, he is relatively at rest, and the satellite is, since it is revolving, so in satellite, the satellite atomic clocks are going to witness time dilation. What? It's going to witness time dilation. Means time will be passing slower in these satellites. So that's why in these satellites we do have atomic clocks, and these atomic clocks are adjusted from time to time. Why it is adjusted? So that it can be kept at pace with the time on the earth. And why that is important? Because like we are using GPS technology. GPS, global positioning system. It is used for navigation purposes. We locate different locations. You use for Ola, Uber and all, you book a ride. So the thing is like driver is coming at, after how many minutes it is going to come, how many minutes it's going to take. So it talks about distance also, it talks about time as well. So GPS technology is very, let's say, useful technology for the entire world, right? It's a very important technology. And there has been a story also, like, related to how the technology was built and like, which companies were associated. There is a Hollywood movie associated with that. The GPS technology, how it was being built, Google Earth, right? So that's the thing. GPS technology is beneficial for the entire world. That's the thing. And like, there are various things associated with this. So did you understand about the spatial theory of relativity, its significance, length contraction, time dilation, mass energy equivalence? Having understood this, now let us move to another important theory, right? Let us now quickly move to another important theory. This is known as general theory of relativity, right? So there are some examples also that I have discussed with you. We are going to give printed notes, so you can read those examples from there. Yes.
Length contraction में कोई application?
Length contraction के बहुत सारे applications हैं. मतलब as of now, length contraction is perceived. Perceived means actually length of the object will not be contracted. It is perceived in case of bigger objects. But when we talk about particle accelerators, in particle accelerators, particles are accelerated to very high speed, right? Very, let's say, near to the speed of light. So then they experience that the particles show different properties altogether. And when we talk about nanotechnology, later on we will be having a unit which is nanotechnology. There we will discuss about, let's say, like at nano scale, when you go to a smaller scale, right? The properties of the particles change altogether. So at large scale, let's consider like, this is the thing, it has some properties, right? If we make it smaller, the properties that it is exhibiting now, it will automatically change. So that is size dependent, volume dependent it becomes. We'll discuss about that thing, okay? So as of now, we can consider it to be a, hypothetical concept, which the length contraction, right? So next one, like yesterday we discussed a question also that was related to which of the following is the reason why astronomical distances are calculated in light years, right? So that was speed of light is always same because it has been proposed by Albert Einstein. It has not yet been refuted, and like it has been, in fact, it has been approved through various projects, various experiments across the world, right? This is the thing. Now write down second topic, topic number 2. Anyone having any question during the discussion, you can always ask, right? So it should be interactive. Now this topic is general theory of relativity. General theory of relativity. So here now we need to understand that the general theory of relativity was also postulated by, it was also given by Albert Einstein. It was also given by Albert Einstein. In which year? He has given it 1915. So after 10 years, after a decade, he has come up with general theory of relativity. And here also he published a research paper, okay. Name of the research paper is important for us, okay. He published a research paper. Write down name of this research paper. It is known as the foundation of the general theory of relativity. The foundation of the general theory of relativity. The foundation of the general theory of relativity. This is the research paper that Albert Einstein has published in 1915. And through this research paper, he talked to the world, he proposed his idea of general theory of relativity. And I'll talk about, let's say, like, since he has given general theory of relativity in 1915, in the year of 2015 or 16, right, like already people have built experimental, let's say, setup, and they have actually, let's say, like they were able to detect gravitational waves. Like here we are going to talk about gravitational waves. They were able to detect after 100 years of this thing, right? So the thing is, long back, so he was a theoretical physicist. Albert Einstein was a theoretical physicist. I mean, like, he was not given Nobel Prize for a special theory of relativity or general theory of relativity, because Nobel Prizes are awarded for experimental work that people do. Okay, although there can be, let's say, theoretical foundation, then it should be backed up with experimental work, and like people can be together awarded Nobel Prize. There can be, let's say, 2 people, 3 people sharing the same Nobel Prize. It has happened, right? So the thing is, when we are reading science and technology, it is also important for you to keep a tab, to keep, let's say, checking which Nobel Prizes are being awarded, like to whom, for what work they have done. That's also important, because in UPSC prelims exam, UPSC has time and again asked questions in the prelims exam that has a direct relevance with the Nobel Prizes that are awarded to people. So it is important for you to keep a tab on that as well. Okay, this is the thing. So he has published this research paper, the foundation of the general theory of relativity, in 1915. And so write down about it, write down few lines, then I will explain in detail about it. Write down the general theory of relativity. The general theory of relativity is a scientific theory, proposed by Albert Einstein in 1915. Proposed by Albert Einstein in 1915. It is a theory of gravity. It is a theory of gravity that describes the behavior of massive objects. And their interaction with the geometry of space and time. Write down in the second paragraph. Anything missed so far? Okay, second paragraph. The key concept in general theory of relativity. The key concept in the general theory of relativity is the idea that gravity is not a force. That acts between two objects, comma, but rather a curvature of space and time, but rather a curvature of space and time caused by the presence of, but rather a curvature of space and time caused by the presence of massive objects now let us understand about, like, focus on the board. Now we will understand this thing. So here we have written some keywords. What keywords? We have written curvature of space-time. We have written about space-time fabric. Okay. So we need to understand what do we mean by space-time fabric. Okay. Space-time fabric. Okay. So let us understand this fabric first, then I will explain the things in detail to you. Let's consider I have a net like this. What? I have a net like this. Net in the sense, like, there are strings. These strings are attached to one another like this. And let us consider these strings are there, let's say, distributed all across the world in the universe. These strings are there. I mean, like, the way that I have paper, this is the paper. Let's consider this paper is actually made up of these kind of strings. And this is known as space-time fabric. Fabric means kapde. Fabric means kapde. So it is like a space-time fabric. This is the thing. So what Albert Einstein says, that if you have a fabric that looks like this, let's say if I draw it in this fashion, if you have a fabric that looks like this, right, like net, okay, if you have net like this, what will happen? Let's consider we have tied this net from poles from all the four sides. Okay, what we have done? We have tied it from all the four sides. Now on this net, what we can do? We can jump on it, right? Similarly, what Albert Einstein said, that, like, the entire space is made up of space-time fabric. There is something which is known as a space-time fabric, and planets or big massive bodies that we have, these bodies are suspended on it like this. These bodies are there. So if you, let's say, if you have a net, and on this net, if you bring something which is of 10 kilogram, so what it is going to do, it is going to bring some curvature. Curvature means ये जो fabric ऐसा दिख रहा है, so, like, from the bottom it will get like this. From the bottom side it will get like this, and the object will be like this. Are we understanding? This fabric is there, and this is the fabric that is kept, and we have brought a ball, big ball, right? Let's consider 10 kg ball, 5 kg ball. Because of this ball, what is happening? The space-time fabric is getting this particular shape, this one, it is known as curvature. What? Curvature of space-time fabric, curvature of space-time fabric. So space-time is getting curved because of massive bodies, big bodies. We can consider it to be planets, Mercury, Earth, any planet, Mars, that you can consider. If you have larger planets, what it is going to do? It is going to make the curvature even more. If you have big planets, let's consider, if I have big planets, so big planets will create more curvature in the space-time fabric. Small planets will create less curvature in the space-time fabric. What will happen? Let's consider this is the space-time fabric. So this is a bigger planet, it has created more curvature, and a smaller planet, what now it will happen? Let's consider on the same net, we have a big ball and we have a small ball also. Like this, small means with less mass. So small with less mass will create less curvature. Big ball with big mass will create more curvature. So the small mass will get attracted to the big one. You understanding? It will slip like this. Are you getting this point? Fabric एक बहुत बड़ा कपड़ा है, Big bodies are there, it is creating more curvature. Small bodies, less curvature. But the thing is, since it is a uniform fabric, so the thing is, smaller balls will get attracted towards the bigger balls. And you're understanding? So this is the idea of Albert Einstein. He says that gravity in the space-time fabric works like this. He says gravity in the space-time fabric works like this. So all the planets, all the heavenly bodies, massive bodies that are there on the universe, the bodies that have big density or bigger mass, it is creating more curvature in the space-time fabric. The bodies which having lesser density, lesser mass, it is creating less curvature in the space-time fabric. And the body with lesser mass are getting attracted towards the body with more mass. Okay, they get attracted towards the body with more mass. And this is known as gravity. So he says that gravity is not a force that acts between two bodies. Gravity acts because of the presence of a space-time fabric, and since these heavenly bodies are creating curvature in the space-time fabric. Are you understanding this point? Question है तो पूछ लो. I'm here. Doubt? Understood? हाँ? हाँ. अच्छा, इसके वजह से. Now, we will understand about, now the question is here what we are understanding that, like, between two bodies there will be force of gravity, right? Like Newton said, force of gravity exists between every two body. He did not give us mechanism how it works. Albert Einstein came with proper space-time fabric theory. He said, like, gravity works because of the presence of space-time fabric. Later on, maybe in tomorrow's lecture, we are going to understand about some laws in physics that explains why planets are revolving around the sun, that explains why moons are revolving around the planets, that explain why, let's say, like, moons are not striking with the planets. Okay, so there are many things that we are going to discuss, but it is important for you to understand this particular thing. Did you understand what do we mean by space-time fabric? Curvature in space-time fabric. When we talk about black holes are considered to be very, let's say, big bodies which have infinite density. Infinite density means very high mass. Let's consider I have a black hole. The mass of the black hole may be million and billion of times that of planet. So black holes will have more capacity to attract other planets towards it. So that's why black holes attract other bodies towards it, and there will be sphere of influence around the black holes. Like, even light cannot pass through it. I mean, like, light will also get trapped. We'll discuss that concept of black hole today itself, but it was important for you to understand the space-time fabric. So now, having understood this, now write down this. Now read whatever you have written under theory of relativity or like general theory of relativity, and let me know what you did not understand. Vidya Paridhi is asking, is gravitational lensing related to this theory? Yes, Vidya. So gravitational lensing is related to this theory. So this will be one of the counterintuitive effect of general theory of relativity. We are going to discuss about gravitational lensing today itself. Okay, just after this we are going to discuss some effect of general theory of relativity, then we are going to discuss about this. So we have written the general theory of relativity is a scientific theory proposed by Albert Einstein in 1915. It is a theory of gravity that describes the behavior of massive objects and their interaction with the geometry of space-time fabric. Okay, so have you understood this thing? डाउट हो तो पूछना, ठीक है, मतलब like it's like that. I'm here to interact with you. हाँ, okay. So we have understood this. Now after this, write down another paragraph. We are going to understand effects of counterintuitive effects of general theory of relativity. Okay, I have just written GTR. GTR means general theory of relativity. Okay, so now write down a line. After writing this, write down a line. The general theory of relativity. The general theory of relativity predicts several phenomena that have been observed. Someone is writing JR gaming sir, views बहुत कम आ रहा है. अरे don't check our YouTube channel. So like we are discussing this thing. Okay. So write down. The general theory of relativity predicts several phenomena that have been observed and confirmed through experiments. That have been observed and confirmed through experiments, including number 1, gravitational time dilation. Gravitational time dilation. Special theory of relativity mein we have discussed about time dilation. Now in general theory of relativity we are adding another word, which is gravitational time dilation. This gravitational time dilation will be little different than the time dilation that we have seen earlier. So write down this thing. Write down first, clocks in a strong gravitational field. Clocks in a strong gravitational field. Clocks in a strong gravitational field run slower than clocks. Run slower than clocks in a weaker gravitational field. Full stop. I will repeat that line, previous line. Clocks in a strong gravitational field run slower than clocks in a weaker gravitational field. Full stop, write down. This effect has been observed in experiments. This effect has been observed in experiments using atomic clocks. Using atomic clocks. Now let us understand about this gravitational time dilation. Okay. So let's consider I have a planet over here. Let's consider it is Earth. I have another planet, maybe Mercury. Which planet is bigger, Earth or Mercury? Anyone? Normal general knowledge. Earth bigger than Mercury? अच्छा ठीक है मान लेते हैं ठीक है. So now see, let's consider I do have two planets. Okay, I'm naming it as like any planet. This is a smaller planet. It has, let's say, like less gravity or less gravitational field. This is a planet that has, let's consider, more gravity. What? It has more gravity, right? So what will happen if I have a clock, right? If I have a clock over here, so this clock in this, it will run faster, and over here this clock will run slower. Okay, the clock will run slower. Where we have more gravitational field. Okay, so this gravitational time dilation means clocks that are located on those objects that have very big mass, right? So more density. There the clocks will run slower as compared to an object, right, on which the gravity is less. Are you understanding? It says clocks in a strong gravitational field run slower than clocks on a weaker gravitational field. This is known as gravitational time dilation. In the time dilation concept, we studied about speed, right? if an object is at speed, so like for him the time will run slower, right, as compared to a object which is at rest. Here we are talking about that if there is a clock in a strong gravitational field, that clock will run slower as compared to a clock which is in a weaker gravitational field. This is the difference, right? Gravitational time dilation. So write down second important thing associated with this, and this is known as gravitational lensing. Okay, write down gravitational lensing. Gravitational lensing. Gravitational lensing. Write down a line. Okay, after this write down a line, then I'll explain this thing to you. It says the curvature of the space-time, the curvature of space-time, space-time single word में लिखेंगे space-time, the curvature of space-time caused by a massive object, can bend the path of light, passing near it, comma, resulting in distorted and magnified images, of distant objects. Full stop. This effect has been observed in astronomical observations. This effect has been observed in astronomical observations. Now let us look at the board. Okay, what is the thing? Let's consider, let's say our planet is located somewhere here, very small planet here, and there are lights. I discussed about that, like, photons got freed when? After the Big Bang. And since then photons are traveling, right, unless they are disrupted somewhere. If photons, if they come in contact, let's say in contact with black holes, they may get trapped also. But the thing is, since lights are coming, so what happens, the massive objects that are there in the universe, right, those objects are able to attract even lights as well. What they do, they distort the path of the light. Okay, they distort the path of the light. Okay, like this. It should have come this way directly, but the thing is, they distort the path of the light. Or we can say it this way. Original path of light was this, it should have gone this way, but it distorts, this body distorts. So the thing is, from Earth, if we are seeing something, so we will see, we consider light to be traveling in a straight line. So if light is coming from somewhere, we will assume that the object is located there. But the thing is, these big bodies, heavenly bodies that are located in the universe, these bodies are distorting the path of the light. They are bending the path of the light. What they are doing? They are distorting the path of the light. And since they are distorting and bending the path of the light, so the thing is, when we calculate the, let's say, location of the body from where this light has emerged, so this gives us error. What? Because of this gravitational lensing. Gravitational lensing मतलब कि जो light है, it appears कि मतलब ये light जो है, it appears brighter. It appears that it is coming from a brighter source. Okay, ये gravitational lensing का मतलब ये lens का we use lens. Why we use lens? ताकि जो चीज़ें हमें अच्छे से नहीं दिखे, lens का use करके we can see. We use lens in microscope also. Using microscope in the laboratory, we are able to see the small fungi and all. We see their structure also. So on those microscope, electron microscope or other kind of microscope, what we are doing, we are enlarging those things, right? So enlarging using lens, and this is known as gravitational lensing. because of gravitational field of objects, the lights are lensed. They appear to be brighter, they appear to be coming from a, let's say, like, more distant object, because from here if we locate, so like if we trace back, like, we'll locate that this object was located here, this object was located there. That is known as gravitational lensing. Is it understood? Gravitational lensing. Okay? So I'll showcase an image also, maybe we might have, yes. So I'll showcase an image related to gravitational lensing, right? So that you can understand that through that image itself. You see here, if we see this image over here, right, if we see this image, what is happening? This is a distant galaxy, this is Earth, right? So the thing is, the lights that are originating from these galaxies, so the lights are getting distorted. It appears that the light is coming from somewhere else, and these lights seem to be magnified also. Okay, this phenomena is known as gravitational lensing. What? This phenomena is known as gravitational lensing. Okay, and gravitational lensing is a real phenomena. It has been observed, and like it is taken into account while doing astronomical calculations. Okay, then we are going to learn about, yes, someone has written something online. Someone is asking, sir, इसे एक बार और बता दो क्योंकि मैं सब्जी बना रहा था. All right, sir, is gravitational lensing caused error in measure Hubble constant? Okay. So Hubble's constant is taken into account while doing this. No, generally it happens. Those people who are, let's say, attending the class from home, they get distracted because, like, they are sitting in front of the computer. And like if someone calls them, if there is a phone, so they will pick that phone, so they will get distracted. So that's why attention in online classes are always less as compared to attention in offline classes. Sometimes people may miss out important things. Okay, so this is the thing. Okay, otherwise same thing is being taught. I am the same person here also, like, that there also you can access. In online classes you face internet difficulty as well. Sometimes internet may be slow. Voice may not come, video may not come, that becomes difficulty. Okay. All right. Okay. Okay. So Dreamer, so someone has asked gravitational lensing. So what is gravitational lensing? Because of the gravitational field of massive objects, right? So the ray of light that is coming, lights that are coming, they get distorted. They seem to be magnified. Okay, this phenomena is known as gravitational lensing, and gravitational lensing causes error also in calculation. And I'll talk about few experiments, right? Today itself we are going to discuss about some experiments. One of the experiment is known as LIGO detector, laser interferometer gravitational wave observatory. So there is an observatory that people have created to detect gravitational waves on the surface of the earth. Right, in USA it is located. So to understand that, we are going to discuss about let's say, like, this interferometry, the principle of interferometry we are going to discuss, and then we are also going to discuss about space based projects, that, like, on the surface of the earth what is happening, we are receiving huge number of signals, different types of signals are coming from distant places, and when those signals are coming on the surface of the earth, they have to travel through the atmosphere, and in the atmosphere gases are there, various disturbances are there. Let's say we do have different layers of various densities, and because of which the signals that we are actually receiving on the surface of the earth, these signals are getting distorted. Right, so that's why, to avoid any kind of error in the calculation that we do, so many scientists, like, many organizations across the world, including NASA, they have planned for some projects which is space based. For example, I'll talk about, so, like, what is telescope? Using telescope, we see distant objects. It's a bigger form of binocular. दूरबीन का बड़ा वाला हिस्सा, ठीक है. So using telescope, what we do, we see distant objects. We do have telescopes that are located on the surface of Earth, but through those telescopes we are observing, but like it is giving us error also. Why? Because atmosphere is a disturbed place. So that's why United States of America, NASA, they have, let's say, like, launched a space-based telescope also, which is known as James Webb Space Telescope. And UPSC has asked a question in the mains exam related to James Webb Space Telescope. Same telescope that is there on the surface of the Earth. So they have, let's say, like, they have created a space-based telescope. So those telescopes are placed on in the space. So from space it is directly receiving the data, there it is doing the calculation, and it is finally sending us what? The final result. That's the thing. Are you understanding? Yes. So like we are going to discuss about ELISA project also today that UPSC has asked in the prelims exam. Okay. So now have you understood about gravitational lensing? Now let us understand about another very important thing which is associated with this general theory of relativity, and this is known as, write down, gravitational waves. What? Gravitational waves. Now we are going to understand what is gravitational waves. Write down here. After writing this, write down. Massive objects moving through space-time. Massive objects moving through space-time can create ripples or waves in the fabric of space-time. Can create ripples or waves in the fabric of space-time, which travel outward at the speed of light. These waves were detected for the first time. In 2015 by the LIGO experiment. LIGO, L-I-G-O, capital, LIGO experiment. Okay, so basically Albert Einstein has told us in 1915, he told that gravitational waves exist. He told that how the gravitational waves are generated. So when massive objects are moving in the fabric of space-time, they create ripples in the fabric of space-time. And because of those ripples, gravitational waves are generated. And those gravitational waves are very feeble gravitational waves. I mean, like, they are not very strong, right? And so in the United States of America, they have created multiple LIGO detectors. One of the detectors is known as LIGO, other is known as Virgo. LIGO stands for Laser Interferometry Gravitational Wave Observatory. Okay, so like this is a kind of observatory for detecting gravitational waves. We are going to discuss about the interferometry experiment altogether. I am going to draw diagrams. You will understand how the interferometry works, right? That's the thing. So basically, Albert Einstein said that gravitational waves exist in 1915. In the year of 2015, using LIGO detector, people have detected that gravitational waves actually exist. And this has led to Nobel Prize. People have been given Nobel Prize for, let's say, creating this LIGO experiment and detecting the gravitational waves. Okay, this is the thing. Now, so having understood this, now let us understand about applications of general theory of relativity. Write down applications of general theory of relativity. Applications of general theory of relativity. applications of general theory of relativity. Write down points. GPS technology. Number 2, cosmology. Number 3, fundamental physics. So just you need to write down GPS technology, okay. So these are the places where let's say we find application of general theory of relativity. Here just you understand, later on you can read from the notes that we are going to provide. So when we talk about GPS technology, how in GPS technology general theory of relativity is used? Because gravitational time dilation happens. Time dilation happens. Because time dilation happens, atomic clocks are adjusted, right? Atomic clocks are adjusted. Not only this, for example, let's consider we have sent Aditya L1 mission. Which mission we have sent? Aditya L1 mission. So Aditya L1 mission is to study the sun, right? We wanted to study the sun. We have sent this mission at L1 point, Lagrange point 1, right? So the timing, we also want to track the timing, that how much time is it going to take for that instrument, set of instrument to move from the surface of the earth there. So we want to calculate the time also. So there must be some kind of atomic clocks, some kind of clocks must be there. So we need to adjust the timing over here. Apart from this, all the missions that we are sending to other planets, like we had Mars orbiter mission, which is also known as Mangalyaan mission. We have sent it long back. So it was, let's say, for the first time India became successful. There are other countries also who have tried for Mars orbiter mission. They could not succeed in the first attempt. We succeeded in the first attempt. We had sent, let's say, Chandrayaan mission as well. So in all those missions, we use clocks as well. And those clocks, timing of those clocks are adjusted by the scientists from time to time, right? Why? So that we can calibrate them, right? So that we can have accuracy in the calculation. So it is used in GPS technology. It is used in cosmology. Cosmology means study of the cosmos. Study of the cosmos means study of the universe as it is. So yesterday I discussed about a scientist. Which scientist? Hawking. Huh? Stephen Hawking, right? So Stephen Hawking, let's say there is a story associated with this, right? Stephen Hawking has been a brilliant student, and he was enrolled in PhD course in, I think, University of Oxford, right? So at the age of 21 years, he was detected, it was detected that he has a kind of disease, and that disease will affect his, let's say, locomotion, means he will not be able to move. So this disease is going to affect his bodily development as well. And so doctors have predicted that after 2 years, he will be able to, let's say, stay alive for at most 2 years. After then, he is going to die. But during those 2 years also, let's say, he has continuously been working on the projects that he had undertaken. He has been doing PhD in some branch of cosmology. So he was doing a study in theoretical physics, theoretical cosmology, right? But the thing is, despite all those things, he has persevered. He has continuously been working, and luckily, let's say, he was able to get proper diagnosis timely, and he lived for long. He lived, let's say, at the age of 21 years, it was let's say, diagnosed long back, but let's say he lived for more than 55 years, and he died in 2018. And that person has also done a study on black holes. What? Black holes. And he predicted, who? Stephen Hawking. He predicted that from black holes also emit some kind of radiation, and those radiations have been named as Hawking radiation. What? Hawking radiation. And as I discussed yesterday, he has published a book also, A Brief History of Time. So that is a very influential book, right, scientific book, right. It's not that easy to read and understand that book, but very influential book of his. So now we are going to, so having understood this, now we are going to discuss about another very important thing, is that Albert Einstein has published this work when? In 1915. So he has given some equations, right, at that point of time he has given some equations. But within 2 years of his publishing this thing, right, there was a person, his name is Schwarzschild. And this person, what he has done, this person has actually come up with mathematical, let's say like, solution for the equation that Albert Einstein had given. And that equation is known as Schwarzschild metric, okay. So now I'm going to write down this thing. So this is associated with the discussion that we were having, and spelling of Schwarzschild is little difficult, okay. So it is SCHWARZ, okay, SCHILD, okay, last one is D, metric. So what is this Schwarzschild metric? Basically, he has come up with mathematical solution, proof of the equation that was given by Albert Einstein in his general theory of relativity, okay. So write down a line about it. The mathematical solution to Einstein's equations, the mathematical solution to Einstein's equations of general relativity that describe the curvature of space-time, around a point mass, I will repeat it, the mathematical solution to Einstein's equations of general relativity, the mathematical solution to Einstein's equation of general relativity that describe the curvature of space-time around a point mass is known as Schwarzschild metric. Write down, it was derived by a German physicist. It was derived by a German physicist, Karl Schwarzschild, okay, Karl Schwarzschild, this is the name, Karl Schwarzschild. In 1916, just few months, I mean like it's not 2 years, in 1916 itself, right, comma, just a few months after Einstein published his theory of general relativity. Write down another line, it is little technical for all of you. The Schwarzschild metric is a solution. The Schwarzschild metric is a solution. To Einstein's equations that describes the geometry of space-time. Around a spherically, comma, around a spherically symmetric, comma, non-rotating mass. Full stop, write down. It is characterized by a number of key features. Including an event horizon. and a singularity. And a singularity. Is that understood? So Albert Einstein has come up with this, his equations of general theory of relativity, and within few months, right, Schwarzschild, okay, Karl Schwarzschild came up with mathematical solution to the equations that he has given. Okay, so this has further strengthened the work that Albert Einstein has done. So Albert Einstein has become famous in 1905 itself after coming up with the special theory of relativity. Then he came up with general theory of relativity. He became an international sensation. Okay, now we are going to understand a very important, let's say, principle related to physics, experimental setup that's going to help us to understand about gravitational waves. Okay, we discussed about gravitational waves, how gravitational waves are generated when massive objects, right, in the space-time fabric, when they move, and also when black holes collide with one another, it also leads to the generation of gravitational waves. And gravitational waves travel at a speed of light, right, but they are very faint. And so we are going to understand how we are going to, let's say, identify existence of gravitational waves. What are the experimental setup that we are going to understand. So for this, write down a heading which is known as laser interferometry. Okay, so this is going to be a topic. This topic is related with the previous topic. It is known as laser interferometry. Okay, laser interferometry. So basically, what is laser interferometry? Using the laser interferometry, we detect whether gravitational waves are present or not. And how do we detect? That we are going to understand through a setup. And for that, we need to understand that here we are using laser light. What light? Laser light. What do we mean by laser light? Many of you may have used laser light in your childhood. छोटे छोटे लाइट आता है रेड कलर का, ऐसे ऐसे करते हैं. हाँ हाँ right. And also they are monochromatic. Generally monochromatic means they have only one color. For example, the light that we might have used, red color light, so it is red color only, monochromatic, right? So many people might have played with laser light earlier. So we are going to use laser light to do interferometry. Okay, so now write down a single line so that you understand about it. Write down laser interferometry. Laser interferometry is a technique. Laser interferometry is a technique. Vidya has written something. Yeah. Laser interferometry is a technique that uses laser light to measure, changes in the distances between objects, with extremely high precision. Distances between objects with extremely high precision. Write down another line. It works by splitting a laser beam. Into two beams. Comma, directing them along different paths. Comma, and then recombining them to create an interference pattern. That can be used to measure small changes in distance. small changes in distance. Now write down a very small line. Few examples of laser interferometry are LIGO detectors, LIGO, L-I-G-O, LIGO detector, capital. And Virgo detector, Virgo. LIGO and Virgo detectors, you can write that thing, or LIGO detector and Virgo detector, like that. Okay. So let us now understand about this concept you have already written, right, about laser interferometry. To understand about laser interferometry, we need to draw a setup, we need to draw a diagram. Quickly let us draw a short diagram, okay. Okay, so see, let's say first of all see my diagram that I am drawing, then you can draw your own as well, right. इसको थोड़ा सा वो थिक कर देना, ये जो this one. This is how the setup looks like, and what are these components? This component is the detector. These components are let's say measurement mirror and reference mirror. This is reference mirror. Measurement mirror, right, and here we have coherent light source. This is coherent light source. So this is how the setup looks like. Now let us understand how it works. Draw this diagram. Just let me know once the diagram is drawn. Done? Okay. Okay. Just take 1 more minute. Okay, all done? Okay, now let us understand what happens. So basically over here, right, I am going to number these things one by one so that you understand. This is number 1, so step begins from here. This is a source of coherent light. This is a source of laser light. From here, laser lights are, let's say, like, generated. Okay. Then over here, we have a splitter. This particular thing is known as splitter. Splitter means it splits the beam of light into 2 equal halves. Whatever light is coming, it splits into 2 equal halves. One half goes to this mirror, other half goes to this mirror. Okay. One light was coming, right? It is divided into 2 parts. One goes here, other goes here. After then, from here, what is the property of mirror? Mirror actually reflects the light. Light is coming, it gets reflected from the mirror. So from this mirror, the light is going to get reflected. From this mirror also, light is going to get reflected. The length of this setup from here to here, let's say from this point to this point, is about 4 km. And the length of the setup, this length and this length is same. What? This length and this length is same. So initially, light comes, it gets divided into 2 parts. And from here, light gets reflected, it comes back here. From here also, light gets reflected and it comes back here. Okay, light gets reflected and comes back here like that. Okay, it comes back here. So again, once it comes here, so this setup is going to see, like, whether the lights that are coming back, they are coming back in phase or not. In phase means whether they're going, the speed of going and coming is same or not. If there is any variance in the let's say phase of the light, so that will be detected by this detector, because after splitting, once it comes back, it goes to the detector, and this detector is able to identify whether there is any phase change, there is any, let's say, speed change in the speed, change in, basically they see change in the length of this particular setup inside this. Okay, so if it is able to detect that, like, there is some kind of phase change or change in the length, so in that case it says that gravitational waves has been detected. Okay, initial laser light comes, it gets divided into 2 parts, it goes here, it comes back, some kind of length it is traveling, it goes here, it comes back. If there are, let's say, gravitational waves, right, if it is detected by one of the detector, so the length, let's say, like, changes, and this is detected by the detector, and this entire setup is known as laser interferometer. And so in United States of America, they have set up, let's say, like, they have set up this thing, it is known as LIGO detector. What? LIGO detector. What is the full form of LIGO? Laser Interferometer Gravitational Wave Observatory. Okay, write down its full name also. LIGO, I'm writing here, okay, LIGO. Laser Interferometer Gravitational Wave Observatory. Is it understood? This is known as LIGO detector, Laser Interferometer Gravitational Wave Observatory. So this observatory has detected the presence of gravitational wave in the year of 2015, and subsequently the people who were involved in developing the setup, right, they have been given Nobel Prize in Physics. Okay, I think in 2016 or 17 they have received Nobel Prize in Physics. Okay, this is the thing. So have we understood? It is a real setup. So I am going to showcase a real setup also to you related to how does this setup looks like. Okay, so this is the image that we have drawn just now. Okay, and this is how the LIGO detector looks like. So this is the center where, let's say, like, you know, from here laser lights come and, like, you know, they are split into two arms. Length of these arms are 4 kilometer. Entire setup is here. I mean, like, it is, I mean, like, we have seen just that way, but these are big buildings over here. I mean, like, there they have, this is known as LIGO detector. This is the entire setup. Okay, so it is 4 kilometer, this is 4 kilometer. Over here they have, let's say, splitter also, they have source of laser light. हाँ, दो ही साइड में. वो लेंथ को देखते हैं, मतलब आपने इधर भेजा सिग्नल, इधर भेजा, इधर से रिफ्लेक्ट होके आया, इधर से रिफ्लेक्ट होके आया, कोई देर से आया तो वो स्लो है, ऐसा हम देखते हैं ना. बट ओवर हियर व्हाट हैपेंस कि मतलब दे चेक द चेंज इन द लेंथ ऑफ, लेट्स से, लाइक, नो, ऑफ द सेटअप ओवर हियर. ओके, मतलब ज्यादा हो सकता है, मिनिमम 2 चाहिए. हम मिनिमम करते हैं एवरीवेयर, राइट? एंड दे हैव डिटेक्टेड दिस थिंग. दिस इज द एक्चुअल इमेज ऑफ LIGO detector, right, which is located in USA. Okay, this is the thing. And India में नहीं है, मतलब, like, actually in India we are building neutrino detectors. We'll discuss about what are neutrinos, right? So we'll discuss about flavors or variants of neutrino also. We have tau neutrino, electron neutrino, muon neutrino. What are neutrinos? We are going to discuss about it. So as of now we have understood about LIGO detector. So where is this LIGO detector located? It is located on the surface of Earth. It is located in USA. This is an experimental setup. I mean, like, you know, real setup. So they have detected also gravitational waves. So having understood this, now write down quickly a heading. We are going to write down a few lines related to LIGO. Laser Interferometer Gravitational Wave Observatory. Heading will be Laser Interferometer Gravitational Wave Observatory. Laser Interferometer Gravitational Wave Observatory. Write down a line. LIGO is a large-scale physics experiment. LIGO is a large-scale physics experiment designed to detect gravitational waves, comma, designed to detect gravitational waves, comma, which are ripples in the fabric of space-time, which are ripples in the fabric of space-time caused by the acceleration of massive objects, caused by the acceleration of massive objects. Write down another line. LIGO made history in 2015. LIGO made history in 2015 by detecting the first ever gravitational waves. By detecting the first ever gravitational waves. Comma, which were generated by the collision of, collision means टकराव होने से, okay, collision of two black holes over a billion years ago, Write down. This groundbreaking, after full stop, this groundbreaking discovery provided the first direct evidence of the existence of gravitational waves, comma, and it confirmed and it confirmed a key prediction of Albert Einstein's general theory of relativity. General theory of relativity. Now write down applications of LIGO. Applications of LIGO. So where do we find application of LIGO? Number one, advancing our understanding of the universe. Number one, advancing our understanding of the universe. Number two, write down, improving our knowledge of fundamental physics. Improving our knowledge of fundamental physics. Number three, inspiring new technologies. Number three, inspiring new technologies. Inspiring new technologies. Now let us move to another topic quickly. This topic is ELISA. What? ELISA. It is associated with the spatial and general theory of relativity that we have been discussing, right? It is associated with gravitational waves. What is full form of ELISA? It stands for Evolved Laser Interferometer Space Antenna. Okay? Evolved Laser Interferometer Space Antenna. Evolved Laser Interferometer Space Antenna. Okay. This is the topic that we are going to understand. So basically we have understood that LIGO detectors have been, let's say have been developed and they have been set up on the surface of the earth. When we talk about ELISA, ELISA is a space-based model of the LIGO itself. Space-based model means in case of ELISA, the experimental setup will not be located on the surface of the earth. Where they are located? They are located in the space. They will be located in the space. And from space itself, we are going to detect the presence of what? Gravitational waves. Okay, this is the thing. So write down, few lines just. So with this topic will be over. Write down. ELISA is a proposed space-based gravitational wave observatory. Space-based gravitational wave observatory that aims to detect and study gravitational waves using laser interferometry. I am repeating the line. It says that aims to detect and study gravitational waves using laser interferometry. Write down another line. The ELISA mission इसी फॉर्मेट में लिखना है ELISA को, ठीक है? The ELISA mission consists of three spacecrafts that are placed in a triangular formation in space. Comma, with each spacecraft separated by millions of kilometers, separated by millions of kilometers. And other things are similar to like LIGO detector that we have studied. Let us quickly understand how it works. Okay, let's see, like this is the space, the entire place is a space. So in this space, what we are going to do, we are going to put three spacecrafts, and these three spacecrafts will be separated from one another by millions of kilometers. Means like they will be having equal distance from one another. Let's consider if it is 1 million kilometer, right? So this arm will also be 1 million kilometer. This arm will also be 1 million kilometer, like that. Okay. So they will be located in this space. So from this space, right, they are going to detect gravitational waves, and they will follow the same principle that is being followed by LIGO detector on the surface of the earth. And we know, like, you know, speed of light is about 3 into 10 raised to power 8 meter per second. So light travels very fast. So using this setup, basically they want to detect what? They want to detect the presence of gravitational waves. So this is a space-based antenna. Its purpose is to detect gravitational waves. Is it understood? Now we are going to move to another topic, right? This is going to be the next topic, very interesting. Now we came to a very interesting topic, and this topic is black holes. Write down. Black holes. Write down a definition of black hole, then we are going to discuss. You have already understood about special theory of relativity, general theory of relativity. It will be very easy for you to understand about black holes. Write down a definition. Black holes are astronomical objects. Black holes are astronomical objects with extremely strong gravitational fields. With extremely strong gravitational fields, comma, so strong that nothing, comma, not even light, can escape from them. Full stop. They are formed when massive stars run out of fuel and collapse under the force of their own gravity. I am repeating the line. They are formed when massive stars run out of fuel. They are formed when massive stars run out of fuel and collapse under the force of their own gravity. So now let us understand about this. Long back when this Big Bang happened, after then, I mean, like explosion happened, within few seconds lot of things has happened, and after 3,80,000 like years after black hole, so like, you know, the universe started cooling down, right? Things started escaping from there, and like photons escaped from there, okay? And then they have escaped in the form of gases. I mean, like, you know, gases in the sense that were having very high temperature. So over the time period when they were moving away, right? So like because time, let's say because temperature was low, slowly and gradually these gases consolidated, and these gases led to the formation of planets. They led to the formation of stars. Planets means, like, if I talk about Earth, in the interior of the Earth, inside the Earth, what is there? We have molten form of lava. I mean, like, things are in the molten form. Very high temperature we find inside the Earth, And apart from this, they are made up of nickel, they are made up of iron, etc. Like, if you go to the middle of the earth, you will find everything in molten format, but they are solid. They are metals, right? They are solid and very high temperature. Like, if we come to the surface of the earth, on the surface of the earth, temperature is low. So what it explains that initially when earth was formed, at that point of time, it was formed like out of a very high temperature thing, right? They have solidified over the time period. So the outer shell of the earth is kind of solid. It has lesser temperature as compared to inner. If you go inside the earth, there are, let's say, thousands of degrees centigrade inside the earth. Similarly, if we see composition of other planets, inside other planets also there are similar composition. What? I mean, like inside those planets, very high temperature it is found. And if I talk about the stars, stars are those things that could not consolidate the way that planets have done. So what is happening on the surface of those stars now, let's say, like, nuclear reactions are happening, nuclear fusion reactions are happening. For example, on the surface of our sun, nuclear fusion reactions are happening. It is emitting huge amount of energy every day, all the time. Reaction is happening, right? And we are receiving maybe, like, very less than 1%. I mean, like very small percentage of energy we are receiving from the sun. And for earth, sun is the ultimate source of energy, because from sun we are receiving the heat energy, we are receiving the light energy, and we are converting it into various forms of energy to meet our energy demand, right? To let's say function our day-to-day things. So the thing is, when on the surface of the sun, when reactions are happening, what is actually happening? Mass is getting converted into energy. Means Albert Einstein had given an equation, E is equal to mc square. So mass is getting converted into energy. So, like, a small amount of mass is generating huge amount of energy. But slowly and gradually what is happening? This mass, right, the mass that is there on the surface of the sun, so those like it is disappearing, because it is converting into energy, and that energy is going in all direction. So after some time, this star or the sun will, let's say, like, collapse. Means it will run out of energy. It will collapse. Once it collapses, what will happen? I mean, like, no further nuclear reaction will happen, and the thing is, like, it will solidify, it will become a dark object, and then it will have very high density. So when we talk about black holes, so black holes are like that. Okay, black holes are of the size 1,000 times that of sun, or million times that of sun. Means, like, they are very big size things. But over the time period, they have also run out of energy, because, like, these reactions has happened, right? On all stars, like these kind of reactions happen, because, like, from there we receive light. So when the stars run out of energy, they collapse, right? They form black holes. Why we call it black holes? Because, let's say, like, let's consider earlier, this was the star, right? It was radiating energy on all directions, but after running out of energy, it solidified, right? It solidified, it became a smaller mass, right? It became a smaller mass, and after solidifying, it has become black hole. Black hole means even if light tries to travel near to it, light will also be captured. Means, like, they have so much gravitational field that even light will be captured. So, like, there is a region around the black hole, there is a region around the black hole. Let me draw this region, right? Let's consider this is the region, and inside this region, if anything comes, that will be trapped. Okay, inside this region, if anything comes, that will be trapped, and this region is known as event horizon. This region is known as event horizon. Okay, and the center of the black hole, over here, the center of the black hole, the whole mass is concentrated over there at the center of the black hole. That is known as singularity. What? It is known as singularity. Singularity is the central point of the black hole, where we have infinite density, we have infinite gravitational pull, right? Event horizon is the area surrounding the black hole, right? If anything comes in this area, it will be trapped inside the black hole because of the gravitational field, right? If things are moving, let's say outside it, maybe let's say it experiences lesser force. This is known as black hole. And so around black hole there are many things, okay? So there is a around black hole, let's say like, beyond event horizon, what happens? Let's consider this is event horizon. Beyond event horizon, what happens? This yellow line I told, event horizon. Beyond event horizon, what will happen? I mean like, there are gases that are still rotating around it. So this swirling mass of gases, forms a disk which is known as accretion disk. Okay, this forms a disk, and this disk is known as accretion disk. What? Accretion disk. Okay, this is known as accretion disk.
These are made of gases.
Yes, these are made of gases that are revolving around the black hole. But as soon as they are, let's say, coming near the event horizon, they will get trapped. It's like that. They are rotating and like, they will be trapped. It's like नदी में होता है ना कुछ, मतलब ऐसे ऐसे चलते चलते, हाँ वैसा. This thing happens. हाँ, huge amount of research are going on around black hole, but people have come up with experimental proof, so many things that like, black holes exist. अंदर क्या होता है? अंदर तो लाइट भी नहीं भेज सकते. लाइट भेजेंगे, लाइट भी चला जाता है उसमें. हाँ. So, his questions are very valid. So basically, how we infer it, for example, let's consider I have a ball. मेरे पास एक ball है. If I throw this ball on the wall, it is going to come back. It is going to make some noise. So, like, since it is coming back, so I can consider that the wall is solid. By hearing the noise, I can consider that what is the quality of material that is there on the wall. If it is, let's say, like the wall is made up of some iron, it will make separate noise. If it is made up of wood, it will make separate noise. So the thing is, what we do, we see the effects of the things, and on the basis of effect, we consider that what should be the property. So the thing is, in the universe, they have identified that there are places where light is going, where light is coming, so it is like normal place. There are places where light, everything goes, and like, there is no trace of it. So they have named it as black hole. Okay, they have named that even light can get trapped inside it. Okay. Huh. And it is because why it happens, we have discussed about what? Space-time fabric. Albert Einstein. Albert Einstein has said, in the space-time fabric, the massive bodies are creating curvature in the space-time fabric. So if a body has huge density, it is going to create more curvature. Since it has more curvature, it will attract the smaller bodies near it. Okay, all the bodies that come in the contact of event horizon, they will be trapped in inside the black hole. Outside, they may go like that. This is the thing. Like tomorrow also we are going to have discussion. Tomorrow I am going to talk about why planets are moving. In a circular fashion. Not in circular fashion, they are known as elliptic orbit. We will understand about that also. So this is the thing. Have you understood the concept of black hole as of now? So here I am going to showcase, let's say, some regions related to black hole. Okay, some regions related to black hole. So today we are going to try to draw a diagram quickly. Okay, we are going to draw a diagram as well. So like we have seen this thing, let's say around black hole this happens. We are quickly going to draw a diagram. So all of us, let's say, will try to make a diagram of black hole. Let's consider this is the place which is singularity, where we have singularity, and from here, let's say we are going to draw some lines. it becomes little tricky after this. Draw this diagram, try. Means like this is not the perfect diagram, but this is singularity, gravitational space-time distortion. And this region is known as quiet region. Negligible gravitational influence. Okay, drawn this region. Now, did we understand what do we mean by singularity? Singularity was where mass of the black hole is concentrated, and why it is lower, because like it has caused deformation on the space-time fabric. It has caused curvature in the space-time fabric. That's why it is here. And then this region is known as event horizon. So if something comes nearby event horizon, it will be trapped inside the black hole, right? If they are outside this region, that is known as quiet region, so it will be having negligible impact on this particular object, right? So this is the thing, and this is gravitational space-time distortion. This is the thing. So in black hole we have singularity, we have event horizon, we have, let's say, gravitational lensing also happens. Gravitational lensing, right? We discussed about it, that like lights coming nearby, so it will get distorted. Some lights will be trapped, some lights may go that way. Apart from this, Hawking radiation is important. I discussed about it. So Hawking radiation, like, so where do we see Hawking radiation? For this I will showcase an image to you, okay. So in that image you will be able to identify that, like, radiations are emerging, so that is known as Hawking radiation. So even from the black holes some kind of radiations are jets are coming up, right. So that is known as Hawking radiation. So write down write down few definitions: singularity, event horizon and Hawking radiation. We will understand. Write down first of all singularity. First point, singularity. A singularity is a point in space. A singularity is a point in space and time where gravitational pull of a black hole becomes infinite. Pull of a black hole becomes infinite and space-time itself is infinitely curved, and the space-time itself is infinitely curved. Write down, full stop, after then, at the center of a black hole. At the center of a black hole, comma, it is believed that there is a singularity. It is believed that there is a singularity where the laws of physics as we know today, break down. Number 2, write down. Next, event horizon. This we are going to write down definition of event horizon. The event horizon is the boundary. Around a black hole. Beyond which nothing, comma, not even light can escape the gravitational pull of the black hole. I am repeating the entire definition of event horizon. The event horizon is the boundary around a black hole beyond which nothing, comma, not even light can escape the gravitational pull of the black hole. Full stop. Then once an object crosses the event horizon, it is considered to be trapped inside the black hole. Third, write down third point, Hawking radiation. Hawking, Hawking, Hawking radiation. There are many things associated with black hole. However, I am going to give a booklet so you can use. Write down. According to the theory of quantum mechanics, comma, black holes emit a form of radiation called Hawking radiation, comma, which is caused by the quantum fluctuations of space-time near the event horizon. Okay. Now we are going to understand about another thing is composition of the universe quickly. Okay. So like you don't need to write much. Okay. We are going to understand the composition of the universe. So it is considered that the universe is composed of three important things. One is normal matter. What? Normal matter. Things that we can see. Planets, stars, black holes, etc. Normal matters. So the visible part of the universe that we can feel, we can see, we can predict, right? So that consists of around 5% of the total universe. What? 5% of the total universe. Apart from this, there is another thing that is known as dark matter. What? Something which is known as dark matter. So what is dark matter? Dark matter means the invisible part of the universe that we cannot see directly, but we can see its effect, because without the presence of dark matter, right, without considering dark matter to be present, we cannot explain other parts of the universe. For example, the planets are moving, where they are moving. I mean, like there must be something, right? So there they are saying that, the part of the universe that is not visible to us, right, that is dark matter. Why not visible? The thing is, let's say, there are some of the things that interact with light. For example, if we throw light on something, right, that thing gets illuminated. Illuminated means we can see the effect of light on that object, that object can be seen. But there are matter, like where, let's say, even if you pass the light, this matter does not interact with light. We will not be able to infer the presence of that matter using electromagnetic radiation. They do not interact with light, they do not interact with electromagnetic radiation, and that's why they are called as dark matter. Okay. So dark matter is composed of around 27% of the universe. How much? 27% of the universe is composed of dark matter, right? This is the thing. Then we have another thing, which is third part, is dark energy. What? Dark energy. Dark energy. So what is dark energy? Basically, like in the universe, there are some forms of energy, means like energy is there which cannot be seen, which cannot be, let's say, its impact cannot be seen. That is known as dark energy. And dark energy consists of about 68% of the universe. How much percent? About 68% of the universe. So if I draw a kind of disk, right, if I make a percentage of the things, क्या बातें कर रहे हो आपस में? हाँ, अच्छा बुरी आत्मा है. Okay, so this is part of, let's say, dark energy around 68%, right? Normal matter around 5%. And this is dark matter around 27%. ठीक है? Dark energy, we'll see. Dark energy मतलब there are energy in the universe, energy format. ठीक है? मतलब which cannot be that like human beings are not able to understand. The human beings are not. देखो होता क्या है कि देर इज, यू माइट हैव हर्ड अबाउट कि वेव पार्टिकल डुअलिटी. देर आर समथिंग दैट एक्ट्स समटाइम्स एज पार्टिकल मैटर, समटाइम्स एज वेव. ठीक है? व्हेन इट अज्यूम्स द, लेट्स से, फॉर्मेट ऑफ मैटर, दैट इज नोन एज मैटर. ठीक है? अदरवाइज इट विल बी कंसिडर्ड टू बी पार्ट ऑफ एनर्जी, लाइक दैट. वो डिफरेंस है बस. And the thing is, like when we talk about modern physics, we will have a discussion on modern physics. There will be a class. There we will understand that, there are forces, and these forces lead to the creation of matter. Matters also get created, ठीक है, तो that we are going to understand in modern physics, ठीक है, so we will have discussion related to that. So dark energy is a mysterious form of energy that is thought to make up approximately 68% of total energy content of the universe. It is called dark because like dark matter, it does not interact with light or other forms of electromagnetic radiation, making it impossible to observe. So we are quickly going to solve 2-3 previous year questions. It will hardly take 1-2 minutes, right? हाँ, ये दो क्वेश्चन क्विकली हम देखेंगे. फर्स्ट क्वेश्चन सो वी हैव ऑलरेडी सॉल्व यस्टरडे. यू हैव सेड स्पीड ऑफ लाइट, राइट? सेकंड क्वेश्चन. सो read this question quickly. So I am going to make it bigger for those people who are okay, who are online. Maybe I'm just. So is it readable? Consider the following statements, right? Light is affected by gravity. Second, universe is constantly expanding. Third, matter warps its surrounding space-time. Which of the above is or are prediction or predictions of Albert Einstein's general theory of relativity? 1 and 3. हाँ. 1, 2 and 3. Tell me, मतलब be loud. See, general theory of relativity में we have understood about gravitational lensing. Gravitational lensing में क्या होता है? Light is affected, it is distorted. So light is affected by gravity, distorted by gravity. The universe is constantly expanding. General theory में उन्होंने नहीं बोला है कि universe is constantly expanding, but the thing is like because of Albert Einstein is also assisting us. Big Bang हुआ है, Big Bang में बताया है कि मतलब like it is universe is constantly expanding. Universe is constantly expanding. Albert Einstein has talked about gravity कि कैसे है, मतलब like you know, so it is let's say like you know Albert Einstein का भी role है इसमें. There is role of it, although we have not discussed in detail about it. Albert Einstein also has role, but like we have got to know this thing that universe is constantly expanding from Big Bang theory that we have discussed. ठीक है, Big Bang से हमें समझ में आया matter warps its surrounding space time. वाप्स मतलब स्पेस टाइम कर्वेचर करता है, मतलब लाइक ऐसा होता है ना, ऐसा, ठीक है. सो इट शुड बी डी, ठीक है. बाकी देख लेना, इट इज अ प्रीवियस ईयर क्वेश्चन. यू सी लाइक इन प्रीवियस ईयर दे हैव आस्क्ड दीज क्वेश्चंस. इट मींस यूपीएससी आल्सो वांट्स यू टू स्टडी लेट्स से लाइक यू नो दीज डीप कॉन्सेप्ट्स. अरे देन आई हैव अनदर क्वेश्चन. Although I got the material made, but like you know in the material some portion is let's say got hidden inside an image. This is another question. Quickly we will solve this question, okay? Recently scientists observed the merger of giant black holes. क्या? Scientists observed merger of giant black holes billions of light years away from the earth. ठीक है? What is the significance of this observation? We have observed कि merger of black holes happened. Higgs boson particles were detected, gravitational waves were detected, possibility of intergalactic space-time travel, wormhole was confirmed. It enables scientists to understand singularity. Gravitational waves, ठीक है, were detected. Basically क्या है? Black holes जब merge करेंगे, so they are going to emit gravitational waves. And LIGO detectors से we have identified that gravitational waves exist. अभी जो आपने लिखा भी था कि LIGO detectors, ठीक है, मतलब it has identified that black holes have merged. So B is the right answer in this case. ठीक है. So this is the thing, and there is a short concept. I'll take 1 minute. That is known as scientific social responsibility. What do we mean by scientific social responsibility? Basically, those people who are scientists, those people who are working in scientific institutions, and the scientific institutions itself, they do have a responsibility towards the society. What kind of responsibility? To educate the common masses, right, about developing scientific temperaments, solving the societal problems through scientific means. For example, when we talk about, let's say, global warming is happening. So people are coming up with scientific solutions that how global warming can be reduced by reducing greenhouse gases, right? By reducing the emission of greenhouse gases, by going for carbon sequestration. So the thing is, when institutions, scientists, engineers play a role, right, in solving the societal problems, right, that is known as scientific social responsibility. I have included a paragraph over here, means like entire page related to this. So you can read about it. So that's a concept basically. And so the Department of Science and Technology, last year, I think, like, few years back during COVID or before COVID year, it has come up with a white paper that talked about scientific social responsibility. Okay, so that's a concept. Okay, scientists do have responsibility towards the society. The way that we hear about corporate social responsibility, we know about CSR, corporate social responsibility. So corporates are actually helping the society, like, they are donating fund, they are doing this thing, that thing. So similarly, scientist does have a responsibility towards the society. That's the thing. Okay. हाँ, मतलब Department of Science and Technology has come up with white paper. I have read it long back, so I thought of discussing this concept with you. Okay, so they have printed the booklet, although they have printed, but like, some portions got inside, I mean, like related to the composition of the universe. So it got inside the image. Otherwise, other things are included. So you will get today's class notes here printed. Yesterday's class note I'll give you, let's say, like, tomorrow or some other day, because I yet need to compile it. Okay, that's the thing. So any questions from today's class? ठीक है, समझ में आ रहा है आप लोगों को? बिल्कुल हिंदी में बात करते हैं, हमारे लैंग्वेज में है. हाँ, स्पीड ज़्यादा हो जाती है. अच्छा, ऐसा ठीक है, मतलब लाइक अच्छा नहीं, मतलब देखो बात ये है. Thank you so much everyone who participated online. We'll take your questions. Maybe you can ask your question in the comment section. So we'll take your question at in next classes. All right. Thank you so much.